Okay, everybody. What we need to do right now is we need to do a recap of what we learned back in CNT 120. Cover some things that are on our that we're going to do a kind of pretty heavily in CNT 125, and one of those obviously is going to be doing addressing on our network. Now, we don't really play around the whole heck of a lot with the MAC addressing, that portion of addressing on our networks, but we will be going pretty heavy with IPv4, IPv6, DNS, things that make your networks actually work. So I'm not going to talk a heck of a lot about being able to find a MAC address on your computer. You should already know how to do that, but we'll cover it real quick and then move on from there. We will talk about setting up TCP/IP on your computers. You're going to do a small lab on setting that up this week. So, we want to make sure that we're ready to go and be able to do some things on our computers that a lot of times when we get to certain levels, we kind of take them for granted. We're going to look at the ports. Those are very important because that determines when we write our access control lists and set up our firewalls. And then what they're called sockets when we have an IP address and we have a port combined with each other. We're going to look at DNS. We're going to look at the domain name resolution. We're going to look at some command line tools that you're going to use to troubleshoot. We use them often. I was on a command line just today just to determine some things in my classroom. Haven't been here for a while. We've been doing virtual, and now we're back in the building. And, there's some things that I had forgotten, you know. So if we go all the way back and we look at Chapter 1, you learn that the OSI model is used to describe pretty much everything that we do in computer networking. It's set up so that the modules of the OSI reference model, for those of you who don't remember, it's, please do not throw sausage pizza away. P for physical, D for data link, N for networking, T for transport, S for session, P for presentation, and A for application. And at each individual layer, we've got different things that we got to be able to troubleshoot. You saw that as we work our way up or down through the 7 layers of the OSI reference model, there's different things that are happening to our mail as it goes on through. In Chapter 2, we looked at the different things in the network's infrastructure and looked at the documentation and maintaining and troubleshooting a network. You designed a network in CNT 120. You designed the racks. You set up switches, stuff like that. In Chapter 1, we also looked and we talked about like different addressing methods at the physical and data link layer, and then how those addresses work their way up the OSI reference model. If we go back to the data link layer, the layer in which our switches actually operate, switches themselves utilize the MAC address. The MAC address is that address that is burned into every single network interface card. It's a 48-bit hexadecimal address. It's represented in groups of what we call hexadecimal numbers, typically separated by colons. And I will say typically because those sometimes when we look at them, they'll be separated by a hyphen. Okay. It's also called your physical address. So your MAC address, your data link layer address, your physical address, and you will also hear it called at times the Ethernet address. A lot of people get that confused. Then we have our network layer addressing. Now there's 2 types of network layer addressing. Now those are our IPv4 addresses, which is a 32-bit dotted decimal address. So for example, you might have an address at home on your computer. If you were to open up a command prompt right now and you would do type in ipconfig, all one word, all lowercase, you might see it says 192.168.1.52. And then it'll have a subnet mask paired with it. Please remember that every network address, every 32-bit IP address must be paired with a subnet mask. And we'll get into that later on when we start actually working with subnetting, which is going to be a very detailed chapter that we're going to have to do together. And I think what I'm going to do to really help us get through that, I have a lot of things on video and I have everything already set up, but I thought maybe I might set up a GoPro and do one on a giant whiteboard to kind of teach you guys how to do things. But we'll see what we have prepared, and we'll see if you guys are struggling or not. But the network layer IP address is a 32-bit dotted decimal address represented as decimal numbers separated by a period, dotted decimal. Then you have the IPv6 addresses. It's a 128-bit address, and it's 8 blocks of hexadecimal numbers. This was set up because we were running out of IP addresses. So we came up with another solution. It is a much more efficient way to network versus the IPv4 addressing. For some reason, people just aren't grabbing hold of it. It's actually easier to set up. We don't have to subnet it. I think what people don't like about it is it's just a lot more numbers to try to remember. 192.168.1.1 is a lot easier to remember than 2001:0002 ABCD 124C. It's just too much. And then we have something called transport layer port numbers. Now, what we got to remember about a port number is that a port number is used to keep track of the applications that are being used. So, for example, my IP address might be 192.168.1.56, but I'm sending some email right now. So 192.168.1.56:25, because 25 is the simple mail network protocol identified by a number, 25. So that's how those things are kept track. And then at the application layer, we have things called an FQDN, which stands for Fully Qualified Domain Name Service. Now, what that does is on my network, it keeps track of computer 1, computer 2, computer 3, computer 4. I'm not going to remember that computer 1 is 192.168.1.64, and that computer 2 is 192.168.1.53. Those numbers change. But it would be nice if the computer remembered that it was actually called computer 1, computer 2, or computer 3, or computer 4. So that's how that works. Like, I don't know the IP address of Microsoft, but the DNS servers know the IP address of Microsoft. Okay. Now, a fully qualified domain name, like say for in a classroom, might be computer1.cnt.hack.edu. That would be a fully qualified domain name. Now, so let's go back and we'll talk about our MAC addresses one more time here. It is a 48-bit hexadecimal address. As you can see, like right here, burned into the network card, is a unique number. There are not supposed to be two MAC addresses alike. I have heard stories that someone said they had a duplicate MAC address on their computers, and it was a mistake by the company. A MAC address can be spoofed to make them to give you two identical ones, but typically you're not supposed to see two identical MAC addresses. The first 24 numbers, okay, the first 24 bits of a MAC address are supposed to be unique to the manufacturer. And then the second 24 bits are supposed to be unique to the card. and this makes up your 48-bit MAC address. Now we have dynamic addressing and static addressing. So I can tell you right out of the gate that my server in my classroom is 192.168.100.8. It has been 192.168.100.8 for about 15 years. I set it up that way. Why I chose 8, I don't know. But the fact is, I statically assigned it, which means I permanently etched it into the system. I went into my TCP/IP settings and I set it to be that. Dynamic addressing is when it's set up automatically. So, for example, on my server, I have what's called a DHCP server. Now, that means it's going to dynamically assign a unique address to different nodes in my network. So if I have 500 computers in my network, I will have a pool of addresses set up that will go out. So things like my printer, my servers, okay, they won't receive an address dynamically. They'll be statically assigned because I want those to always be the same. But the people who are logging on periodically on my network, I would like for them to get unique addresses. So I have those all set up dynamically. So I keep a pool of addresses for them. So they'll get an address when they log on, and then 8 hours later, when they're logged off, their address will go back into the pool. Okay, and we'll talk about DHCP in a little bit later on. The TCP/IP settings on my computer can be found in a number of different ways. The easiest way that I have found to get to the to those settings is to right-click the little network icon on the lower right corner of my taskbar by the clock and choose Open Network and Sharing Center, and then I'll go to my settings that way. Now we'll notice that we always have an IP address, and I mentioned that it's always going to be paired with a subnet mask. A subnet mask is used by the router to identify which network your computer belongs to. Then I'll have a gateway. And the important thing to remember about what a gateway is a gateway is a node on my network, typically my router, which allows me to get out of my network. It allows me to leave the network. That's what a gateway is. So and it's important because there are certain addresses that we have on our networks that don't work on the outside world. So the address that say I got from Verizon, or the address that I got from CenturyLink, or the address that I got from Comcast, okay, for my router, that address works on the outside world. The inside address, okay, if I'm running a Comcast network, it might be a 10.1.10. something. That address doesn't work on the outside world, so I have to translate that address into the public address. Maybe it's 50.42.32.16. I don't know. That 50.42. whatever, that address is my gateway. That address is how I leave. Now, on my Comcast network, my 10. network can only talk to my 10. numbers. So my address might be 10.1.10.1. That might be my gateway address. That is the address that I use to talk to the device that lets me escape my network and go to the outside world and get to the internet. I also have a DNS server out there. Now, this is a node or a device that's whole job is to translate the name of a node to an IP address. See, routers and computers, they don't know names. They don't care about names. They know numbers. So there's a node out there that knows where the website is for hack.edu, that knows the website of dcts.org, that knows the website of microsoft.com, that knows the website of amazon.com. It knows the numbers between those two, and that's called a DNS server. Now, if we want to find out what our address is, it's real simple. Okay, all I have to do is go to a command prompt and type IP config, just like that. And as you can see, that I have a number of different addresses. In my wireless LAN adapter, my address is 192.168.100.57. I typed in ipconfig. If I'm on a Linux machine, I don't type in ipconfig, I type ifconfig. That's easy enough. As I mentioned earlier, the IPv4 address is a 32-bit dotted decimal address. Those addresses are broken into 4 groups. Okay, these are a decimal number, 72 dot, see, dotted decimal. Okay, so when you're talking to IT people, I don't want anyone to say 72 period, 56 period, 105 period, 12 period. It's 72.56.105.12. The numbers only range from 0 to 255, which is how we count up to 8 bits. Okay? Some IP addresses are reserved and cannot be used. For example, the 10 dot addresses are private. The 172.16 all the way to 131 are private. The 192.168.0.0 to 192.168.255.255. These are all private addresses. These are what we normally see inside of our networks. Okay, we have 5 different classes of networks: A, B, C, D, and E. A, B, and C are what we use. You and I are using to connect to the real world. Okay, D, okay, is for multicasting and multi-groups. Okay, and then E is for experimental use. Okay, these addresses here begin with 223 or 224. Sorry, 224. Okay. If we were to give an idea of why we ran out of addresses, if you figure there's 7 billion people on the planet, okay, if we were to say, okay, I've got 16 million addresses on 126 of these networks, I got 65,000 on 16,000 of these networks, and I have 254 addresses on 2 million of these networks. That's just not enough addresses if we are taking into consideration the number of IP addresses you yourself are using right now. Now think about that. How many addresses are you using? Well, you might have a Fitbit or a smartwatch, right? Or both. You've got a phone. You've got a laptop. You've got a tablet. You've got a Switch. You've got a Wii. You've got an Xbox. You've got a PlayStation. Then you take a lot of the other things into consideration that you may have that you probably didn't realize you were using that are using up IP addresses, like your smart TVs, your Roku devices, your smart home, your light bulbs, if you have a smart home. Okay, all those, your Google Nest, your Amazon, your Echo Dots, okay, all those are using up IP addresses. So it's pretty easy to understand why we all ran out of these addresses. As I mentioned earlier, the class D and E are not available for general use. D begins at 224 and goes all the way to 239. It's used for multicasting. To get a good grasp of what you think multicasting might be, multicasting is used when we have multiple computers or nodes that are going to be communicating with each other in a group-like session. So another easy way to think about it is, think about when you're playing at Xbox Live and you're playing Call of Duty or some other multi-user game. Okay, you're using something similar to a multicasting event. Okay? Government and research is used at 240 to 254. Another address that you're currently not going to use is the 169.254. Now this is your API PA address. Some people call it a PIPA. I don't care what you want to call it. But it's an automatic private IP addressing. So if we think of it this way, your computer is designed to talk to your DHCP server or your router and say, hey, I want to get on the network, give me an address, and they gave you 192.168.1.57. It got it automatic. But what happens if the server that's supposed to give you that address isn't available? Your computer says, I'm supposed to have that address, please give me one. So it needs to have something in its place, and it's going to give you something that starts with 169.254.0. something, or 169.254.255. something, all the way up through those numbers. It's a lot of numbers. It's 64,000 numbers, 65,000 numbers. So your computer, those numbers don't work on the internet, but your computer was told it had to have an address. So this number was this range of numbers was automatically given so that you will have that number. Now, as I mentioned earlier, those numbers that we have, the 192.168 numbers, the 172.16 numbers, the 10 dot numbers, they don't work on the internet. So how is it that right now you're on the internet, you're watching this video? Well, we've taken your number and we've translated it. We've converted your number to the one lone public address. Now think about that. I'm in a building right now where there's 1,000 users, and I can take all their 1,000 IP addresses that are private, and I can push them all out, all of them out through the one public address very easily. That's network address translation. How do I keep track of all of them? Well, I use ports. So this guy's doing mail, this guy's doing web, this guy's doing YouTube, this guy's gaming. You know, everyone's doing something different, or they're doing something similar. So what I do is I'll take port numbers, either a dynamically created port number or a static port number for a particular application, and I'll append it, I'll attach it, I'll apply it to the end of their IP address, and that makes what's called a Windows socket. So if you can see here, I've taken that port address translation. So I got a 10.1.120:80. They're doing web. 80 is the port address for the World Wide Web. Okay, and I'm sending them out to 92.52.44.1, which is the web server, and I'll give this guy a dynamic address of :8000. Okay, and then the next guy, I'm going to give him 8001 because I have to be able to keep track of all these conversations that are occurring simultaneously. That is what port numbers are designed to help us do. Okay? There are a bunch of different ways that we can do this. I can do static NAT, okay, which means this address here is going to use this IP address to go out, or I can say this guy here, I have a pool of addresses and we're just going to share them with the group. That's dynamic NAT, okay? Which takes us then to IP version 6. Now we look at that address, 2001:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000:000 :9C5A:00CC. It's a lot to remember, and nobody wants to do that, so we get all confused and we say, we hate IPv6, but in the grand scheme of things, when we start doing subnetting, you're going to love IP version 6 because it's so much easier. I can look at that number and say, this number is a global address. This number right here works on the internet. I can look at that number and say, because it begins with 2001, it's a global address. It's huge, yes. We can make them smaller, okay? We can eliminate certain groups, okay? Because it makes it easier. Right? We can eliminate preceding zeros. So we can make that 2001:0:B80, then actually get rid of that group of zeros right there and say ::D3, :9C5A, :CC. I can make it easier, but what's really important is that this was developed so that we don't run out of IP addresses. Now I know we're sitting back saying, well, we didn't think we were going to run out of IP addresses last time. We actually knew right away we were going to run out of IP addresses, but we used it anyway for some stupid reason. But this makes 360 undecillion. So it's 360 and then tack 36 more zeros on the end of it. That's how many IP addresses we have. So we should never run out. And if we do, let's hope it runs out before, or after my time expires and I don't have to learn something new. So like I said, we can eliminate the preceding zeros to make it smaller. So as you see down here, 2001, : we got rid of these preceding zero here, okay? And then we kept those guys together. That's one way to do it. It's not the way I would have done it, okay? I would have done it this way, okay? Now, in this one here, they could have also eliminated these 3 zeros and just put 1 0 in. The : can only be used one time, so you use it to get the most benefit. So I was able to eliminate the 10 zeros that were right here. See, 4, 4, and then those 2, so those 10. I eliminated those 10 with just those 2. If I use the : here, I got rid of those 4, but then I had to keep these. So I could have gone 0, : 0, there. So this one here is the fuse number 0, so yeah, that's the preferred method. And we'll talk about that again when we get into the higher end numbering. Okay, there's different words we want to like vocab that we need to get a hold of here. One of them in IPv6 is a link. Okay, now the local link. See, when we look at our IP addressing, if we do an IP config, you're always going to have 2 IPv6 addresses. One is the IPv6 address that we use to talk to all of our devices inside of our network, and one that we use to talk to devices outside of our network. So if you ask yourself, well, this is supposed to be easier, why do I have to have 2 addresses? Well, if you're going to be talking to everybody in the outside world, do you really want them to have a chance to talk to your inside network? Do you really want that guy, anyone to be inside your network? No. So we keep a private set of numbers inside, and we keep a public one on the outside that talks to your inside numbers. Okay. Dual stacked is a term used when you're using IPv4 and IPv6, because not everybody's running IPv6 yet. And if we're going to use IPv6, okay, over an IPv4 network, well, we have to find a way to package that data and send it through the IPv4 tunnel until we can reach an IPv6 network, and that's called tunneling itself. And if we were to break down our numbers, since it is 128 bits, if we take the first 64 bits of our network and we split it into 2, the first 64 bits is going to be the network number. The second 64 bits is going to be your MAC address. It identifies your node. So the interface ID is the second 64 bits, the second half of your IPv6 address. That, folks, is your ID, your interface ID. Now, 2 or more nodes that are on the same link, we just call them neighbors. It's easy enough, right? A unicast address is that address that just goes to one individual. Global unicast is an address that is specific to another node on the internet. It can be routable. It's routed. If it goes across a router and out to the World Wide Web, it's routed. Your link local is the address that is specific on your individual network. A multicast address, okay, addresses that go to multiple individual or multiple nodes on a network, okay. And any cast can go to identifies multiple destinations with packets delivered to the closest addresses. And there's just an example, and they're all pretty similar. So, how do we identify the different types of IP addressing for IPv6? We really just want to look at the first block. So if we take a look at the first block here, and then you see the first prefix being 3. So the prefix being 3. So it's 2000, and then you got the 01. So these last 3 bits. or because you actually read from right to left, so 1, 2, 3, or the first three here. So this is always going to be a 1, so 2001, 3001 global unicast address. FE80 is always going to be a local link, and then when we see the FF here in the beginning, in hexadecimal, this is as high as you can count, and that's as high as you can count, so I'm encompassing everybody right there. So I'm going to have multicast. I'm talking to a group. Right. IP, just as with DHCP and IP version 4, you can do auto configuration with IP version 6. It'll set up for your first two. What's really cool about it, as IPv6 works, the computer will always check to make sure that the IP addresses are not actually used anywhere else on the network before it just doles out and gives you yours. So next, we want to look at port numbers and sockets. As I mentioned earlier, port numbers are used to identify applications, but they're also used to keep track of all simultaneous conversations that are occurring on the network. When I pair my port number with my IP address, we call it a socket. Okay. Now there are different types of port numbers, and there's thousands of them. Well-known ports are from 0 to 1023. Register, which means it's an application, this application will always use it, like a Symantec port. Those are from 1024 to 49,151. And then other ports that are either private or dynamically generated, maybe for your BitTorrent clients, stuff like that, those go all the way up to 65,535. Okay. So once again, this is just an example here of a telnet session that's going on. Telnet is port 23. There's a lot of ports that you're going to just need to know out of the gate: 80, 21, 20, 21, 22, 23. Those port numbers, 25, you should always know what they are. 1, 2, 3, which is a network time protocol. You just need to know those. Okay. Protocols that we haven't covered yet: TFTP. It's a UDP protocol. It's typically designed for transporting small files quickly. Network time protocol used so that your servers and your computers are always acquiring the same time. If your times are incorrect, then what ends up happening is you won't be able to transfer data. So, for example, if I'm at July 6th at 2 o'clock and your computer is July 10th at 2 o'clock, we are literally on different times, so we might not be able to transmit the data. I'll give you a perfect example. I had a client who couldn't get her Verizon email. It called me out, and I'm trying to troubleshoot. Okay, and I'm looking at things like the SMTP server and the IMAP server. I'm making sure all those addresses are right, and then I noticed that her clock is wrong on her Windows computer. So I reset the clock on her Windows computer, and everything starts working again. Reboot the computer, and her clock reset back. She had a dead battery in her laptop, so it was resetting the BIOS clock. And then Windows on boot up would look at the clock on the motherboard and said, oh, it's 2001, 1201, January 1st, and then it would set the Windows clock to be that. If she were to be running a network time protocol, her computer would be able to then sync up with a Windows clock somewhere or an atomic clock, set its time appropriately, and she wouldn't have that issue. But fortunately, all I had to do was just change the coin battery in her laptop, and all was fine. LDAP is directory access, so it's what keeps track of usernames, computers, and printers on the network. SMB, server message block, it's more of a transport protocol. SIP is used for like video and phone conversations, along with H323, which is your video compression protocols. As I mentioned also earlier, DNS, character-based names and IP addresses. I need to keep an IP address associated with Microsoft.com. I need to keep an IP address associated with computer1.hack.edu. Okay, my fully qualified domain name. Domains names, and there's top levels, different domain levels. And what a lot of people don't understand is these guys right here, ARPA, MIL, INT, EDU, Gov. Okay, these are top level domains. Now ICANN, the Internet Naming Authority, they restrict who can have these. So believe it or not, high schools don't get EDUs, colleges get EDUs. Okay? So here's some standard, typical, top level domains. Okay, so a .com. Okay, it's that one on the end. It's not Google.com. Okay, Google will be the next level. Okay. Each organization that provides host services is responsible for providing and maintaining its own authoritative servers for public access. Okay, so Google has its own authoritative service. Okay, so each organization that provides host services, that's important. Okay, hack.edu doesn't provide host services for organizations, so therefore they are not responsible for being their own authoritative server. But if I get my services from Google, Google is my authoritative server. Okay. There are 4 types of DNS servers. We have primary DNS. Okay. That's the authoritative name server for an organization. It's what holds the main databases. Okay. My organization here has a DNS server, and it keeps track of all the internal stuff. So Google doesn't know about computer1.hack.edu. Okay. Google knows about hack.edu, but doesn't know about the internal devices in there. Our servers at Hack maintain that information. Then we're going to have a backup server. Okay, we have caching DNS servers, which just stores information, and then we have forwarding clients. So, for example, if I want to go out to say TNT.com, and my server doesn't know where TNT.com is, it will then forward my request off to another server that should know where it is. Okay. And there's an example of some authoritative servers. These are organizations down here that offer servers, so they then have their own, okay, their own these are their own authoritative servers, and then it's like UA and MDC. They belong to EDUs. Craigslist, it's an organization. PBS, an organization, and then these are your .coms over here. Okay. Different types of records that we have with DNS. We have A records. A record is just the name of a host. Okay, and here's what's weird. If it's an IPv6, it's a quad A record. Okay, canonical name is an alternate name for a host. Okay, just another name. Okay, if we need to do what's called a reverse lookup, usually for DNS security reasons, that's a pointer record. Another important one to remember right here is the MX record. So, for example, we have hack.edu, which takes you to our website, or dcts.org, which takes you to a website. But then we also have your mail server. So my email address at mbridgehouse@dcts.org or msbridge@hack.edu. That mail server is a completely different server that has a completely different purpose. It's what gives me and hold on to my mail. So that's my MX record. So when something is going to have that @ symbol in front of it for mail, then it's going to be looking for my mail exchange server. Okay. Different types of server software here. The open source one here for your Linux and your Unix boxes. Microsoft has their built-in DNS in their Windows servers, which work very well. And then you've got, if you've ever heard of it, the DMZ. It's an area between 2 different firewalls. It's just like open area on the internet. It's fair game for anyone to attack. Troubleshooting problems, okay? In Windows, you just want to hit the event viewer. So a really easy way to get to the event viewer, just hit your Windows key, you right click your Windows key, and you can go right to your event viewer there, and it'll tell you everything that's going on with your computer. Now, please understand that these are very, very detailed. So you want to be looking. Some of them are just giving you information, and others are giving you errors. So you want to look up your errors and then pay close attention to your timestamps. Commands that you might want to use during troubleshooting. Some of the easiest one that we use is the ping command. It's the best way to find out if I have connectivity to a device. So for example, you open up a command line and I might say ping, what did I say my server was here? 192.168.100.8, and it'll tell me whether or not I'm actually have connectivity. If I don't get a reply from with a byte count and a time, then I didn't get it. If it goes through and says, you know, unresolved host or something like that, those are not successful pings. You want to get a reply from the device you pinged, not a reply from your computer saying host was unavailable. You want to make sure that you have a reply from the node you were attempting to ping. The IP config we talked about earlier, that was for Windows. IF config is for your Linux. NS lookup is to find out where a DNS item is being resolved and who the authoritative servers are. And you use the same thing if you're doing Linux. ICMP is the protocol that you are seeing when you see your replies back. Okay, so a lot of companies, you might be trying to ping a particular server and it might be coming back saying there's no response from the host. It doesn't mean that the host wasn't available. What it might mean is that the host is not responding with an ICMP packet, the Internet Control Message Protocol. Because if I had to spend my time responding to pings, that means I'm not responding to other important network information. And if that is what's happening, there could be what's called a denial of service happening on my network, and I have to be cautious of that. I had a student years back who was a very good gamer, and during the midway through the game, in many cases, uh, other players would attack her node and give her what's called denial of service. Now, it's illegal to do a denial of service, just so we all know that. But they were giving her a denial of service and would kick her out of the game if she was achieving too much. So I taught her how to, on her router, how to block or turn off ICMP messages, and then other players were no longer able to kick her out of games for that reason. The same thing works on IPv4 as it does with IP version 6. The big difference is you just want to use ping 6 on a Linux machine, or you can do a space -6 on a Windows machine, to be specific. And there's just some examples of how it would look. There's an example of an IP config that I've already shown you before as well. IF config has some commands that you can add to it as well. To get information, you have if config-a, gives you all the information associated with the Linux interface. You can bring the interface up and bring it down. When you make changes in Linux, it's important to remember in Linux, if you're going through the command to make a change in the IP address, you have to bring the interface up and bring it down before the changes will take effect. On a Windows machine, you have to make sure you click through all the OKs. And this lookup I mentioned earlier allows you to query the DNS database from any computer on your network, find out authoritative servers, and stuff like that. And that's what you're seeing right there. You can change DNS servers from within interactive mode with the server subcommand, and then specifying the IP address of the new DNS server. The dig command is used on Linux and Mac operating systems. It's important that we remember, especially for those of you who are Mac people, you will use ifconfig instead of ipconfig. If you're doing tests on your own devices, you will use dig instead of nslookup. Macs run a Unix kernel, which is almost identical to Linux, just that the Linux is free in Mac and the Unix is not. Okay. If you have an incorrect time, you can just do you can run a command prompt and enter W32TM space/query space/source. You'll find out where you're getting your time information, where you're syncing up your times. If you're getting the wrong IP addressing, you might want to check to see if you're getting a DHCP. If you do an IP config on your computer, you will see if you have DHCP turned on or off. Okay. You also, if you're in charge of the DHCP server itself, and people are having issues, you might want to check to see what your DHCP scope looks like. Now, the scope means how many addresses do I have in my pools. And also, the scope would cover how long someone's going to have that IP address. Now, I've run into this problem with customers of mine who own restaurants, and they offer Wi-Fi in the restaurant. When they get their systems, their routers are set up to dole out an IP address for typically 8 days. Well, not too many people, as far as I know, will spend 8 days inside of a restaurant. So if you've got 50 addresses available for your restaurant and your lunch crowd comes in, and hopefully you did 50 people at lunch, they leave, the dinner crowd comes in, and they can't get on Wi-Fi because the people who are at lunch have the IP address assigned to their devices. So what you do is you reduce the least time that a user will have that IP address. So you make it 20 minutes. You're in there for 20 minutes, you leave, your address that was assigned to you goes back in the pool for someone else to use. When you're on a network and you hit 50% of your lease time, your node will automatically request to renew the lease after 50% time is up. So at 20 minutes becomes 30 minutes, and 30 minutes becomes 40 minutes, and so on. Here's where static assignment can get you into trouble versus dynamic. When you do it dynamically, everybody's getting an IP address that's different and unique, and they're all getting the exact same subnet mask, and they're all getting the correct gateway. When we do static IP addressing, you might think you're going through and making every device correct and setting it up appropriately, and you might be doing that, but it's very easy for you to get a typo. Very easy for you to lose track. So you're a computer 253, and then you go to the next room and you're trying to think to yourself, well, it's the last one that I did. Oh, it was 252, so now you have two computers of 253. So duplicate addresses, the way they work on a network is one device will win and one will lose. One device will get on the network, one will not. If you have the wrong subnet mask, that means your IP address might work, but you might not be able to communicate with anybody on the network because your subnet mask is used to tell the router what network you belong to. And if you're on a wrong subnet mask, you're not on the right network. You won't be able to print. You won't be able to get to the server. You won't be able to get to the gateway to get to the internet. Your IP address is working on your computer, but it's just working for you. And that brings us to the conclusion of this chapter. Hope you all got something out of it. And I will see you for chapter 4.